High Redshift Universe, the IAU, the same organization that voted to change the categories of our solar system objects and created the dwarf planet, well, they just voted, and I voted on this myself, to rename the Hubble Law to the Hubble-Lemaitre Law. And I'm going to tell you what that's all about a little bit here. First of all, what is the Hubble Law? Well, the Hubble Law came about in the early 1900s. Hubble had been measuring distances to galaxies. Another astronomer, Slipher, had been measuring velocities of those galaxies. And Lemaitre was actually the first one to publish a plot of velocity for a galaxy versus, or a bunch of galaxies versus distance. So you take a galaxy's distance and you plot it against its velocity. The velocity is on the vertical axis. You can see Lemaitre, you kind of can see a relationship here. He plotted a line through it. And the further away a galaxy is, the faster it seemed to be moving away from us, which is a little bit of an odd result. And then Hubble came along a couple of years later in 1929 and did a similar plot. His is a little cleaner. You can see that the relationship is linear. And there's a good relationship there, which is why we named it the Hubble Law. But Lemaitre had done it earlier. It was in a kind of an unknown journal or a smaller journal. And when it got republished in English, they dropped some of the plots. I don't think it was anything nefarious going on. It probably just was an editor saving paper, who knows what. But the realization that he had done it before Hubble and kind of concurrently with him is being honored now. Now, what is this? What's the big deal here? What does this imply? Well, it implies that the universe is expanding. And I'm going to do a quick demo here. I've actually brought a supply of air, and I have a balloon here that I can blow up. But I recommend my colleagues up here plug your ears, because it is awfully loud. Careful with the I've drawn little galaxies. Now, if we pretend that the balloon is the fabric of the universe, we're going to scaring you a little bit. So I'm going to stabilize the universe here a little bit and aim it at you. Now, keep your eyes on one dot on the balloon. So that's the actual noise the universe makes as it expands. Now, it's a little easier to watch in reverse. So pretend this is the universe now collapsing. If there were enough gravity in the universe, it could switch this expansion and collapse it. But now watch one galaxy and watch all the others look like they're moving towards it. But if we pick a different one, it looks like all the galaxies are moving towards that one. So it doesn't matter which one you're living on. Now we can turn my mic back on, because I'm not going to make horrible noises. So the fact that it looks like all the galaxies are moving away from you is just, it's an artifact of the universe we live within. It isn't the fact that you're at the center of this explosion, which is why I so greatly dislike animations of the Big Bang that make it look like it's an explosion coming from one spot, because it's not. Now, the value of the Hubble constant, why is that important? The Hubble constant's important because it tells you how quickly the universe is expanding. And at first, Lemaitre had a value above 600. Our current value is about 10 times smaller than that, so that was really, really wrong. And the values dropped rather rapidly. In fact, these values were so high, the age of the universe was smaller than the age of the Earth. So we had this problem of the Earth being 3 billion years old about, and the universe could only be 2 billion years old at that rate of expansion. So it turned out some star clusters were misinterpreted as stars. It makes the galaxies much further away than they were. So the value dropped rapidly until in the 1960s, you think things are going pretty well. But for those of you that know the history, it wasn't going that well. Measuring the distance to galaxies is very, very difficult. You actually use redshift, just what Laura was talking about. You can measure how much those lines move. If a galaxy is moving away from you, those spectral lines that are imprinted on the galaxy's spectrum get shifted to the red. The faster it's moving, the more they get shifted. So that's the easy measurement. You can get the velocity super, super simply. It's the distance that's hard. We use our eyes. We use what's called parallax to get distance in our brains, and we even use that when out measuring distances on the Earth. You can do triangulation. We do that with the Earth going around the sun. We can watch stars. Their positions change ever so subtly. For galaxies, however, they're too far away. You can't see them wobble as the Earth moves. Instead, you need a standard candle. So here I've shown candles. The further away they are, they both get smaller in size and they get dimmer. And if you know how bright that candle really is, you can just say, well, it looks so bright, and it must have dimmed this much. It has to be that far away. So that's the basic idea. So if you have an object that tells you how bright it really is, and you could measure how bright it looks in the sky, well, you know the distance. Luckily, there are such objects. They're called Cepheids. They're stars that pulsate. And this chart tells you all about how we use those. I'm not going to go into too much detail here. We could spend an hour on this one. But really, all you need to know is to get a distance, to get the Hubble constant up here at the top, there's many steps. And we like to call this the distance ladder. Now, it's not a ladder where each rung is straightforward, but you can notice some of these methods up here, like if you want to use the planetary nebula luminosity function. We're going to spend 45 minutes on that. But notice it's calibrated using other methods. You have to take steps to get up there. So astronomers realized that this is kind of complicated, and you can have errors all over the place. So you have to be very careful about how you measure these distances. And in fact, throughout the 60s and 70s, there was a big discrepancy between what was being measured. One team was measuring values close to 100, and another team was measuring values that were closer to 50. There were some folks in the middle in there, but the major big-name astronomers, de Vaucouleurs and Sidney Vandenberg and Sandage and Taman, they were really well-respected astronomers, and yet they weren't getting the right answers.
And may I just throw in that it's also of paramount importance to the age of the universe?
Yeah.
So the factor of 2 difference in their in the Hubble constant is a factor of 2 distance in the age. One was saying the universe was 10 billion years old. The other was 20 billion years old.
Yeah.
So big difference.
Yeah, it's a really big difference. And we were starting to get ages of globular clusters that were somewhere like 14, 15 billion years. They're not that old, actually, but it was making it look like the smaller age numbers couldn't be correct. We wanted a bigger number. But along comes an idea of, well, maybe we should build a space telescope. And one of the design constraints was, let's make it big enough that we can measure these pulsating stars that tell you their brightness. It's like a wattage stamp on them, all the way out to the Virgo cluster. So we're able to use the Hubble Space Telescope. One of the reasons it's named that is it was going to nail the Hubble constant to within 10% of its value. So hooray, this is going to be solved. A team of astronomers got together in Aspen. It's a big location where a lot of theorists hang out during the summer. So the observers went there to have a conference about the Hubble constant, sort of clue in the theorists. But they also got together and they wrote a proposal. Now, none of the 4 astronomers that were sort of the old guard, the respected, they had young scientists working with them as well, but they didn't join this team. These were just a group of astronomers that decided they would propose for this key project. There were several key projects that the Hubble Space Telescope was designed to do. Well, these folks' proposal was accepted. These are the ones that were able to do it.
Wendy Friedman?
It is Wendy Friedman and Barry Medor, John Hookra, a whole bunch of groups. Sandy Faber was in there, Garth Illingworth, I could name a bunch of names. Anyway, this was one of their diagrams, and it looks a lot like that distance ladder I was showing you. And they went in and analyzed the error sources, and sure enough, they could show that both of the groups, the group that was getting values near 100 and the group that was getting values near 50, both of them, it was understandable. The errors were large enough that you could get that wide of a range, and they had a plan for making sure they made measurements that were accurate enough to get that value within 10%. And this is sort of letting you see their thinking. Again, Cepheid period luminosity relationship, but they're using several other distance measurements, and they're really using Hubble to the best of its capabilities to beat down these errors, as we like to say. And indeed, they did that, and they got a value of 72. Imagine that. One group wants 50, one group wants 100, and the value that Hubble measures ends up being pretty close to the center, right about 72. So we think problem solved. Hooray, we can put that to bed, right? Not so quickly. People continued to measure the value of the Hubble constant using Hubble, a variety of different methods, gravitational lensing, supernovae, things like that. And there's still a little bit of a spread, but they're all kind of in the same ballpark. The error bars are overlapping nicely. Science is progressing. Along comes the Planck satellite, well, WMAP and Planck. And this is the cosmic microwave background radiation, the afterglow of the creation of the universe itself. So this isn't measuring galaxy speeds or distances. This is a completely different way to get the Hubble constant. And it has to do with sort of the distribution of this speckle pattern, how the hot spots and the cold spots, how far apart they are and how they react. In fact, this diagram is a measurement of that. So temperature fluctuations versus the angular scale of them. Well, this wiggle can tell you the Hubble constant when you put in all the physics. And the value they get is 67. Down here, not 73. So WMAP did it first. Error bars are pretty big. But look, it's overlapping with the Hubble Space Telescope error bars. We're fine, right? WMAP, and then Planck did it, another satellite. Error bars are small, so let's believe that. Well, along comes the Gaia Satellite, and it measures very accurate distances to these Cepheid stars that tell you how bright they are, recalibrates that distance ladder again. So it gets those, we're able to recalibrate and get a better measurement than ever before, and it's up here. So it's 73. Consistent with the value that the Key Project team got. Now notice, these error bars are pretty small. These error bars are pretty small. Planck redid their work. They released another map. And in 2018, there it is. The error bars are even smaller. And now these error bars are not overlapping. This is a difference of 3.5 sigma, a 10% difference. This is significant. So now astronomers are starting to worry. Why does the local value we're measuring from the galaxies and the expansion rate not agree with our cosmological models? So measuring, maybe it's the fact that we're in a slightly underdense region of space. Maybe there's just not enough galaxies, and locally things are flying apart faster than they ought to be. So some folks took that into account and said, sure enough, this stuff's maybe moving away faster than it should be. If you add that in, you can account for some of it. And then they also said, Gaia, some of the quasars, very, very far away things, they shouldn't move as the Earth goes around the sun. It's that parallax. As you blink your eyes back and forth, your finger looks like it moves a lot, but the moon and the mountains in the distance don't look like they move much at all. Well, quasars are so far away, they shouldn't move at all. Well, there's this point, it's like an error, a 29 micro arc second difference. Very, very, very small. This team comes along and says, well, if we use that value and we assume it's the same everywhere in the sky, we can account and offset these values and add a new point, and it's right there. So using Hubble Space Telescope and Gaia, they claim they can agree with the Planck value. But look up here, this point, Hubble Space Telescope Gaia. That point up above was from Adam Rees, Nobel Prize-winning astronomer. He took into account the errors of the Gaia spacecraft and used a different model. His offset he's using for his 0 point is different than the one they use. So this red point I've added sure looks like this team kind of tuned it or picked that value out to make these numbers agree. They got it from another paper. They just didn't invent it themselves. So it was from a completely different paper. But the fact they adopted that, it kind of sets off red flags for me. And I want to see if people can verify it. But this argument over what the Hubble constant is and what the value of it is not over. Science is progressing. We know it to a higher degree of accuracy than ever before. But the number we get from cosmology isn't the number we're getting from the local galaxy flow, and we're just not really sure what it is. It's better than ever, but we're still working on the value of the Hubble constant.